So, this is my contribution to the mega favorite numbers trend currently going on YouTube, started by Brady Heron and some others. I'm going to be talking about a number related to Champernowne's constant. I call it Champernowne's big number after Champernowne's constant. And I have not seen it discussed often on the internet, and so I just thought I'd bring about a little bit of awareness with this event. And here we go. So for those uninformed, Champernowne's constant is defined as being 0.12345, etc., to 8910111213, all the way to 9899100 etc., going through all of the counting integers. So we'll have to start with explaining a certain fraction which very accurately approximates Champernowne's constant. And you can write it with the pattern of 0.123456789 plus 0.00000000101101, etc., with infinitely altering between 1 and 0, and then also adding on to it. And of course, the reason this bit is important is because after the 89, this adds a 101010. Our next bit, 0.000000000000102030405, etc., which does not go through counting two-digit numbers, by the way, or it does. It'll eventually get to 100, which carries over into the previous number, increasing it, almost like addition by columns. Now the reason, and so of course that will, combined with the 101 pattern, give us 1011, 1213, etc., hence accurately approximating Champernowne's constant. Now, luckily for us, these terms can of course be approximated rationally. The first one, very obviously, just by 123,456,789 divided by a billion. But these other two, of course, are repeated ones, so their fractions are not as obvious as immediately, but it can easily be worked out with a bit of math here, as we can see. If we have the pattern of 0.0101, like back down there, but now shifted all the way to the front, so the pattern begins immediately, what we can do is we can multiply it by 100. This will shift all the digits 2 places to the left, which, since the period, the length of the repeating part of the digit of the expansion is 2, and the digits are shifted to the left by 2, it means all of the digits are then lined up one for one. All the ones are lined up and all the zeros are lined up with another 0 from Z to 100Z. And so we can subtract our top number here from 100 times the number, and column for column it will reduce down to 0, leaving us with 1.000, etc., or just 1 as it approaches it with infinitely many zeros. And so from that we can then infer Z, which will be 99Z divided by 99, or original 0.010101, will of course be 1 divided by 99. So that's where we get that. And then of course shifting down, we can then infer, well, what will happen if we do 1 over 99 squared? It will be 1 over 99 over 99, or 0.010101, etc., over 99. Now, of course, what can happen is we can add up all the 1s over 99 together, which would give us the addition of the patterns of 0.000100101 going to the 10 pattern, plus the same pattern, but it takes place 2 digits later, and the same again 2 digits later, and so on. Now, of course, we can see there's only one example where it begins at the leftmost possible digit. So, when we look at the total answer, the leftmost possible digit will be 1. There are 2 times that it happens for the second most left one digit, where there's a 1 there in the addition, so we'll get a 2, and so on. So that achieves our pattern, that achieves our 0.000010203 pattern. So 1 over 99 squared is then the fraction we are looking for. Now, so of course, if we go down then, we know then that each one of these fractions each one of these numbers can then be written as 123,456,789 over a billion, and 1 over 99 times 10 to the power of 8 as our digit, as the pattern starts 8 digits later than it did for 1 over 99. So we need to divide by 10 to the power of 8 to shift it to the proper place. And then for our third term, we have them 1 over 99 squared, now times by 10 to the power of 9 in order to shift it to the proper place. So 1 over all of them added together will be an extremely accurate approximation of Champernowne constant that we can infer due to the carrying over process. We'll count all of the numbers up until 97, and then it will skip 98 to do 99, and then it'll go off on a different pattern. So we can obviously work out the fraction after some computation. We get it to these two numbers, which simplify to 60,499,999,499 all over 490 billion, 50, and 50 million. So this fraction then, what we're now looking for is its continued fraction in our journey to the number. So of course, if we move on, I did the work of working out the continued fraction myself without a calculator just to prove it can be done. Yes, I am in fact, very narcissistic. Do not ask questions. I have, in fact, so narcissistic, I rose above the needs for division lines. Or maybe that's just laziness, probably laziness, which gets us to this final answer of this continued fraction. Now, of course, we may infer, due to how close the fraction is to Champernowne's constant, and also by looking at the last term, if the last term was to increase by a small amount, that would decrease this term, which would once again increase this, decrease that, decrease that. Wait. Point is, if you alternate between the increasing and decreasing as it goes up, it eventually leads to decreasing the value if we were to increase the final term, which of course our term is slightly larger than Champernowne's constant because it skipped the 98 and going straight to 99. So of course we know then that for Champernowne's constant it would have the exact same set of terms as its first term, with then something added to the 15. Now of course, what would the next term immediately be in Champernowne's constant? That would be, I have not written it out, but it would be a term we are going to call n here. And n is then our number that we've came here for, what I'm calling Champernowne's big number. And now I will cue to, with the power of editing, I shall cue to the bit where I show the number. Of course, here it is in all of its glory. I did not work this one out by hand. This is where I threw up my hands. I will not give anyone hope. What I can say though is it can be approximated. To make it easier to comprehend, I wrote approximation here that I worked out with calculator, 4.58 times 10 to the power of 165, which is the number rounded to 3 digits. And for context, this number is between 103 factorial and 104 factorial. So that number is larger than the number of combinations of a deck of cards in like Uno, for example. Anything with less than 104 cards. Okay, I guess I'll have to put something by. This is a horrible outro. Point is, yes. Yay, it's a big number. I've done video. This is first upload. Welcome. I don't know if I'll be doing more content. There's 22 subscribers. You probably weren't expecting this from my snarky comments. Welcome. This is what I do now. Congratulations. Why are we still recording? Help!